Good morning all. We are going to see about AVL tree concept and data structure. So first, what is data structure? Data structure is organizing the element or data in some order efficient manner so that future accessing will be easier. So data structure is broadly classified into two types. One is linear data structure and next one is non-linear data structure. So linear data structure is organizing the element in the sequential order, and it is composed of concepts like list, stack and queue. Nonlinear data structure is organizing the element in the hierarchical or interconnected manner. It is composed of tree and graph concept. Today we are going to see about AVL tree, which comes under nonlinear data structure tree concept. So what is a tree? Tree is a nonlinear data structure in which the elements are organized in the hierarchical manner from top to bottom. In tree we have some basic terminologies like root node, parent node, child node, a leaf node, and for connecting these nodes we are in need of edges. So what is root node? Root node is going to be the initial node which doesn't have any parent node. What is parent node? Parent node will have the child node or children. What is child node? Child node will be having the parent node. What is leaf node? Leaf node has parent but not the child node. It doesn't have any child node, so it is going to be the last level of the tree, last level of node in the tree. For connecting these nodes we are in need of the edges. So in tree we are having some types like binary tree and n-array tree. So what is binary tree? In binary tree, a node will be having at most two nodes, two child nodes. A root node will be having root node, or the intermediate node will be having at most two children. Here n-array node, a node will lead to connection of multiple nodes. We are going to concentrate binary tree only on binary tree, which where AVL tree comes under the binary tree concept. So during the insertion of binary tree, we don't preserve any order during the insertion. So this concept becomes tedious while searching the element in the binary tree. So we are going to the concept called as binary search tree. Binary search tree. Binary search tree is a special form of binary tree. We have a concept that is the first node will be the root node. The first node will be set of nodes. The first node will be the root node. For inserting the remaining nodes, we have to follow the strategy that if we want to insert a new node, we have to check it with the root node. If it is less than the root node, then we have to perform the insertion towards the left side. So if the value that is going to be inserted is less than the root node, it will be inserted as the left child. If the value which we want to insert is greater than the root node, it will be inserted towards the right subtree. The same way, this concept is followed for the searching also, deletion also, right? So in binary search tree, we follow the concept that is during insertion, the first node will be the root node. For inserting the upcoming nodes, we have to check the inserting node with the root node value. If the value which you want to insert is less than the root node, it is inserted to the left subtree, and if the value is greater than the root element value, it is inserted towards the right subtree. But in this condition is preserved for both the deletion and search operation in the binary search tree. But here also we have one disadvantage, that is it leads to the concept of, this binary search tree leads to the concept of left skewed tree and right skewed tree. That is, if your tree grows only towards the left side, that is, you have a root node and all the elements which you want to insert are left than the root node, then the tree grows only towards the left subtree, not towards the, it doesn't have any right children. So this is the concept of left skewed tree. Right skewed tree is, a tree grows only towards the right side. That is, we'll be having a root node and all the values which you want to insert are greater than the root node, then it will be inserted towards the right subtree. It doesn't have any left child or left children, right? So this is the concept called as left and right skewed tree. But in this tree we have a disadvantage, that is the searching, in worst case the searching will be order of n times for both the left skewed tree and right skewed tree, right? So for example, if you take the elements like 1, 2, 3, 4, if you want to insert this element 1, 2, 3, 4 in binary search tree, then you will be performing insertion like the first element will be the root node and the value of 2 we have to check with the root node. It is greater than the root node, so it comes to the right subtree. The value of 3 is greater than the root node, it comes to the right subtree, and the value of 4 is greater than the root node, so it comes to the right subtree. So here the tree grows only towards the right side. If you want to search the value 4, then you have to bypass the value 1, 2, 3 and 4. So if the tree is very large and it is only towards the left or right sided, then your search time is getting increased, that is order of n times. To overcome this, we are going for the AVL tree, which is called as a height balanced tree. AVL tree. So AVL tree is also called as a height balanced tree. So this AVL tree follows the concepts of binary search tree, but the thing is we have to check balance factor during every insertion and deletion, right? So how to check the balance factor? So balance factor is calculated with the formula height of the left subtree minus height of right subtree. So AVL tree is called as a height balanced tree. How to calculate the height of the tree? How to calculate the balance factor? So balance factor, which is equal to height of the left subtree minus height of the right subtree. This AVL tree is same as that of binary search tree, but during every insertion and deletion we have to check the balance factor. While checking this balance factor, it has to be within the limit. Either it can be 0, 1 or minus 1. If the balance factor is not within this value 0, 1 or minus 1, then you have to perform necessary rotations in the AVL tree. There are 4 types of rotations in the AVL tree. 4 types of rotations in the AVL tree. One is LL rotation, RR rotation, LR rotation, and RL rotation. So the balance factor should be within 0, 1 or minus 1. If it is not this value, then you have to perform the necessary rotations in order to make the tree balanced in AVL tree. Now let us go and see the rotations, how to perform the rotations in AVL tree. So first one is LL rotation, RR rotation, LR rotation and RL rotation. What is LL rotation? That is, if you have elements like 3, 2, 1, how we will be inserting this? The first element will be the root node 3, and the balance factor is, you have to check the balance factor after insertion. That is, it is not having any left subtree and right subtree. So the balance factor will be 0 minus 0. The balance factor will be 0. So the tree is balanced. So if you then it comes to left subtree. So the value of 2 is less than 3. So it comes to the left subtree. So here you will be calculating the balance factor once again. So it doesn't have any left or right right child. So the balance factor will be 0 minus 0. That is left subtree, height of the left subtree minus height of the right subtree will be 0. And for here we will be checking the balance factor. The left child we are having 1 left child and 0 right child. So the balance factor here is 0, or that is 1 minus 0. Here we have 1. The balance factor is 1. So the tree is balanced now. So we are having one more element, that is 1. So when we will be checking with the root node, it is less than the root node, so it is coming to the left side. So already we are having 2. We are checking with the root here the value of 2. So the value of 1 is less than 2. So we are inserting as a left child. So now here we are one more time revising the balance factor. Since it is a leaf node, it doesn't have any left or right subtree. So the balance factor will be 0. And for here, the balance factor BF, which is equal to height of the left subtree 1 minus height of the right subtree 0. So the balance factor will be 1. So it is within the limit of, balance factor should be within 0, minus 1 or 1. So it is within the 0 and 1 or within the limit of the balance factor criteria. So next we are checking for balance factor for the root node. So balance factor is equal to height of the right subtree, that is 2 minus 0 is equal to 2. So here it is not balanced, right? So here we have to perform LL rotation. LL rotation is nothing but it is a right rotation. It is a right rotation. How it will be rotated is 2 will come as a root node and 1 will be the left child, and it is rotated towards the right side. This 3 will come as a right child of the root node. Now if you check the balance factor, here the balance factor, here there is no subtree, that is it is a leaf node, so the balance factor will be 0, and here also it is going to be a leaf node, so the balance factor will be 0. And for calculating the balance factor of 2, height of the left subtree, that is 1 minus height of the right subtree, it is also 1, so the balance factor will be 0. Now the tree is balanced. This is called as a left, that is LL rotation. In LL rotation we will be performing the right rotation. Consider you have element like 3, 1 and 2, right? So the first node will obviously become the root node, and for inserting 1 we will be checking with the root node, so it is less than the root node, so it is inserted towards the so before inserting we have to check the balance factor. So the balance factor is, it is going to be a root node, first node, the balance factor is 0, right? There is no left or right children. For inserting 1 we have to check for the condition, that is it is less than root node, so it comes towards the left subtree, right? After inserting 1 we have to check the balance factor, that is Here there is no left subtree and no right subtree since it is a leaf node. So the balance factor will be 0. And we have to update the 0. Now the balance factor is height of the left subtree, that is 1, minus height of the right subtree, which is 0. That is, here the balance factor is 1. Okay. So it is preserved. The condition of the AVL tree is preserved because the balance factor of these nodes are within the range, within the number 0, minus 1 and 1. Now we have to insert one more node, that is 2. We have to check it with the root node. It is less than the root node 2. It is less than, so it comes towards this node, and we have to check the value 2 with the already existing node value 1. It is greater than 1, so it is inserted as a right child. Now we have to check the balance for each and every node, right? So here there is no substitute, there is no child since it is a leaf node. The balance factor is 0, right? And here we have, we doesn't have any left child, we have only one right child. So balance factor, which is equal to height of the left child 0 minus height of the right child 1. So the balance factor is minus 1 here. And for calculating the balance factor of this root node, here we have the 2 left child, that is, these all comes under the left child of 3. So 1, 2. Left child value is 2 minus, it doesn't have any right child, so 0. So here the balance factor is 2. But this 2 is not within the balanced factor of 0, minus 1 and 1. Here the tree is unbalanced. So we have to perform left rotation first and right rotation second. So how we will perform the left rotation? So we have to perform the left rotation like this. So the tree comes like 3, 2 and 1. So this 2 is performed left rotation, and this node will go in between this 3 and 1, the node value 3 and 1. So now we have the tree like, after performing left rotation, 3, 2 and 1. But if you check, you have to perform the balance factor once again. So here the balance factor will be 0, that is left minus right 0, and here the balance factor will be 1, that is balance factor which is equal to height of the left subtree 1 minus height of the right subtree, there is no right subtree, so 0. So here the balance factor is 1. So these both are within the limit of the balance factor 0 and 1, right? If you want to, and you have to check the balance factor of the root node 3. So balance factor of the root node, which is equal to total number of edges in the left subtree, that is height of the left subtree is 2. There is no right subtree, so minus 0. The balance factor is 2. Now it is not within the limit range of, not within the value of 0, minus 1 and 1. So this tree is not balanced. So you have to perform the right rotation. So here the tree changes like 2 will come as a root node, and this 1 will be the left subtree, and this 3 will be the right subtree. Now if you calculate the balance factor for these nodes, you can see whether the tree is balanced or not. So here the balance factor for this root node, for this leaf node 1 is BF, which is equal to, there is no left subtree, there is no right subtree, so 0. There is no left subtree, there is no right subtree, so 0. Here for calculating the node value 2, that is root node, the balance factor which is equal to the height of the left subtree is 1 and the height of the right subtree is 1. So BF, that is the balance factor, 1 minus 1, 0. So 0, 0, 0 for all the nodes, and the 0 is within the balance factor limit. So this tree is balanced now, right? So for LL rotation, you have to perform a right rotation. For LR rotation, first you have to perform the left rotation. You will be getting a left skewed tree, and in order to balance this, you will be performing the right rotation, right? So this is LR rotation. Next, for RR rotation, consider the element 1, 2 and 3. So first element will be the root node. and you have to check, you need to check the balance factor. There is no right sub tree, there is no left sub tree, and there is no right sub tree. So the balance factor will be 0. And for inserting the value 2, you have to check with the binary search tree condition. That is, the value of 2 is greater than the root value 2. So it will be inserted towards the right subtree. Now you have to check the balance factor. There is no left and right subtree for 2. So the balance factor will be 0. For the root node 1, you have to check the balance factor. That is, there is no left subtree, 0. So there is only one right subtree, so -1. So it is balanced. So it is 0 and -1 are within the range of balance factor. It is balanced. Now you want to insert a new node 3. So 3. You have to check this value 3 with the root node. It is greater than 3, so it moves towards the right subtree. Then it is we have to check the value 3 with the 2. It is also greater. Then it is inserted towards the right child of 2. So this is after insertion. This is our 3. So for performing the balance factor, we are having the formula balance factor, which is equal to height of the left subtree, that is 0. No left subtree, no right subtree. So 0 minus 0, 0. Next, for checking the balance factor, there is no left subtree 0. There is only one right subtree, so -1. Here, for checking the balance factor for the node 1, which is the root node, there is no left subtree 0 minus there is 2 right subtree 2. That is -2. Here, this -2 is not within the balance factor range. That is, it is not within 0, -1 and 1. So here the tree is unbalanced. It is a right skewed tree. The tree is unbalanced here. So we need to perform the RR rotation to make this tree balanced, right? So in order to perform RR rotation, we have to perform the left rotation. That is, left rotation is the tree will be rotated like this. And after performing the left rotation, RR rotation means left rotation. So after performing the left rotation, the tree is balanced like 2 will be the root node and 1 will be the left child and this 3 will be the right child. Now it is also satisfying the condition of binary search tree. That is, 2 will be the root node and 1 is less than the root node, so it is placed left side, and this 3 is greater than the root node, so it is placed at the right child. So if you are calculating the balance factor now, here there is no left subtree, there is no right subtree, so 0 minus 0, 0. Here there is no left subtree, there is no right subtree, the balance factor is 0. Here, for calculating the balance factor of this root node, we have balance factor which is equal to height of the left subtree 1, height of the right subtree -1, that is -1, which is equal to 0. Now all the balance factor value is 0, 0, 0. So it is within the range of the balance factor. The tree is balanced now, right? So the last rotation is RL rotation. Consider 1, 3 and 2. Insertion of value 1, 3 and 2. The first node will be obviously the root node, and second node 3 is greater than the root node value 1, so it moves towards right position. And here, and after inserting each and every node, we have to calculate the balance factor. After inserting the first node, there is no right subtree, there is no left subtree, the balance factor is 0. So after inserting, for inserting the root value 3, you have to check the balance factor. So 3 will be inserted in the right subtree. Here there is no left subtree, there is no right subtree, the balance factor will be 0. Here for calculating the balance factor of root node, there is no left subtree and we have only one right subtree, so the balance factor is -1. So the 0 and -1 are within the range of balance factor. Now we have to insert one more element called a 2, right? So for inserting the value 2, we have to check where to place the value 2. So 2 is greater than the root node, so it takes traversal to the right subtree, and this 2 is lesser than the root node, so it is inserted as a left child of 3. Right. So now we have to check the balance, so whether the balance factor, we have to calculate the balance factor, and we have to check whether the tree is balanced or not. So for performing this, there is no left children, there is no right children, so the balance factor will be 0. Here for balance factor of 3, the left children is, we have 1t, the height of the left subtree is 1 and the height of the right subtree is 0. That is balance factor which is equal to 1 minus 0, 1. For calculating the balance factor for this root node, height of the right that is balance factor which is equal to height of the left subtree minus height of the right subtree. Here there is no left subtree, so 0 minus height of the right subtree 2. So it is minus 2. So minus 2 is not within the balance factor range 0, minus 1 and 1. It is not within this value. So we have to perform the RL rotation. So what is the RL rotation? We have to perform the RL rotation to make this tree as a balanced one. So we have to perform R rotation. After performing the right rotation, the tree will be like 1, 2 and 3. It is like a right skewed tree. That is, we have to perform the balance factor one more time. So the height of the left subtree is 0, height of the right subtree is 0. So the overall balance factor is 0. For calculating the balance factor of the node 2, the height of the left subtree is 0 and height of the right subtree is 1. So 0 minus 1, minus 1. For performing the balanced factor of the root node 1, the height of the left subtree is 0 minus height of the right subtree is minus 2. So minus 2 is not within the value of 0, minus 1 and 1, and here this tree is not balanced. So we have to perform left rotation in order to make the tree balanced. So 2 will be the root node, 1 will be the left child and this 3 will be the right child. So now we have to check whether the tree is balanced or not. So 1 minus 1, so height of the left subtree, height of the right subtree, both are not there, so 0. So here also there is no left and right subtree 0, and here the balance factor which is equal to height of the left subtree 1 minus height of the right subtree 1, the balance factor is 0. So all the balance factor are 0 and it is within the limit of 0, minus 1 and 1. It is within the value of the already mentioned balance factor. So it is a balanced one. So for performing insertion and a deletion operation in AVL tree for each and every node, after inserting or after deleting, you have to check the balance factor for each and every node. So if the tree is not balanced, that is, it is not within the range, if it is not within the range of 0, minus 1 or 1, you have to perform the necessary rotation in order to make the tree balanced. So what are the rotations we have? LL rotation. In LL rotation, we will be performing the right rotation. Then we have LR rotation. In LR rotation, first we will perform left rotation and then we will perform right rotation. And next one is, third one is RR rotation. That is, we will be performing the left rotation. And last, fourth one is RL rotation. That is, we will be performing right rotation and then the left rotation. Now we will be seeing the AVL pre-insertion for some sample element, for some example elements. So as I said earlier, the balance factor should be within the range of minus 1, 0 and plus 1. Now let us see the AVL insertion for the set of data like 20, 30, 80, 40, 10, let us keep 60, 50 and 70. let us see the AVL insertion for this given set of data, right? So the first node will be obviously the root node. So the root for the initial only one node, root node, the balance factor will be 0 because there is no left subtree, there is no right subtree. So the first node will be the root node and the balance factor is 0. For inserting the next element 30, so we have to check it with the root node. It is greater than the root node, so it goes towards the right subtree. It is inserted towards the right subtree. Now we have to check the balance factor. So balance factor of this particular node 30, there is no left subtree, there is no right subtree, so the balance factor is 0. For checking the balance factor of this root node, there is no left subtree, so the height of the left subtree is 0 minus we are having only one node, so the height of the right subtree is 1, which is equal to -1. So this tree is balanced again because the 0 and -1 are within the balance factor values. Now we want to insert the third element, that is this is after inserting 20 and this is after inserting 30 and after inserting 80, the first node will be the root node 20, 30. This is a already existing tree. Now we want to insert this 80. So 80 is greater than 20 and this 80 is greater than 30. Now it will be inserted towards the right subtree. So now we have to check the balance factor. There is no left and right subtree for the value 80, the node 80. So the left and right subtree height are 0. So the balance factor is 0. For 30, there is no left subtree. So the height is 0 and we have only one right side tree. So balance factor which is equal to 0, height of the left subtree 0 minus height of the right subtree 1, which is equal to -1. For calculating the balance factor for the root node, the height of the left subtree is 0 minus height of the right subtree is -2. So it is -2. The balance factor is -2. So here this -2 is not within the prescribed value -1, 0 and 1. So here the tree is not balanced. You have to perform the necessary rotation in order to make the tree balanced. So it is like a right skewed tree. So you have to perform the left rotation. So now the tree becomes like 30 will be the root node, 20 will be the left node and this 80 will be the right node. Now we will be checking the balance factor. Now we have performed the rotation. So we have performed the left rotation, that is we have performed the RR rotation, and after performing the rotation we have the tree like 30, 20 will be the left side and 80 will be the right side. So here after checking the balance factor, so here there is no left subtree, there is no right subtree, so the balance factor will be 0. Height of the left subtree is 0, height of the right subtree is 0, the balance factor is 0. Height of the left subtree is 1 minus height of the right subtree is 1, so it is 0. So all the nodes are having the value, balance factor is 0, so it is within the given value. So the tree is balanced now. Now we are going to insert the value 40. For inserting 40, we have to check. The first one is root node 30, the second one is 20 and the third one is 80. So for inserting 40, we have to check it with the root node. So we have to check it with the root node. So it is greater than the root node and we have to check it with the value 80. It is less than the root node. So it comes as a left child. Now we have to check the balance factor for each and every node. So here the balance factor for the node 40 leaf node is height of the left subtree 0 minus height of the right subtree 0. Here height of the left subtree is 1 minus height of the right subtree is 0. So here it is 1. Here for performing, since it is a root node, height of the right subtree and height of the left subtree is both are 0. So 0. For calculating the balance factor for the root node, height of the left subtree is balance factor is equal to height of the left subtree is 1 minus height of the right subtree is 2 minus 2, which is equal to minus 1. So it is within the range of, it is within the, so the balance factors are 0, 0, 1 and minus 1. These are all within the range of the balance factor value. Next we are going to insert the value 10. So here we will be having the tree as already we have 30, 20, 80 and 40. Now where this 10 will be getting inserted? So 10 is less than 30, so it goes towards left side. Here we have to check this 10 value with 20. So 10 is less than 20, so it comes as a left child. Now again you have to check whether this AVL tree is balanced or not after inserting the value 10. So here the balance factor of the node 10 is, since it is a leaf node, height will be 0. Since it is a leaf node, balance factor will be 0. So here for calculating the balance factor of the node with the value 20, height of the left subtree 1 minus height of the right subtree 0. So here 1. Here height of the left subtree 1 minus height of the right subtree 0. So here 1. Here height of the left subtree, for calculating the balance factor of node 30 with the root node value 30, height of the left subtree is 2 minus height of the right subtree is 2. So it is 0. So the balance factor of these nodes are 0, 0, 1, 1, 0. So these all values are within the given balanced factor value. So it is the tree after inserting 10 is balanced now. So now we want to insert the value 60. So we have inserted 20, 30, 80, 40, 10. Now we are going to insert the value 60. So already the tree is having the nodes like 30, 20, 10, 80 and 40 and 40. Now we want to insert the value 60. First we have to check the 60 with the root value 30. So 60 is greater than 30. So it takes traversal towards the right subtree. Now this 60 is less than 80. It takes traversal to the left side. Now we have to check the 60 with 40. 60 is greater than 40. So it is placed as a right child of 40. So 60 comes here now. 60 comes here now. So we have to check the balance factors now. For 60, the height, for checking the balance factor, height of the subtree, there is no height of the, there is no left subtree, there is no right subtree, so 0. There is no left subtree, there is no right subtree, 0. So calculating the balance factor for 40, height of the left subtree, 0, minus height of the right subtree, minus 1, so 1. For calculating the balance factor of 20, height of the left subtree is 1, minus height of the right subtree is 0, so it is 1. For calculating the balance factor for 80, the height of the left subtree is 2 minus, there is no right subtree, so 0, which is equal to 2. But we should have the balance factor as either we have to have as 0, minus 1 or 1 and not other than that. So we have 2. So here the tree is not balanced here right now. So we have to perform the corresponding rotation. So we have to perform the left rotation and then the right rotation. Let us see how to perform. So 30, 20, 10 is already available, and after performing the left rotation, the tree comes like 80, 60 and 40. 80, 60 and 40. So After performing the left rotation, we have like 80, 60 because it is left rotated, and it goes in between 80 and 40, 80, 60 and 40. Now we have to check the balance factor once again. So balance factor here will be 0, balance factor here will be 0, balance factor here is height of the left subtree is 1, there is no right subtree, so 1, height of the left subtree is 2, there is no left subtree, right subtree, so 0. So here the balance factor at the node 80 is 2. It is not balanced. So this particular portion of AVL tree is not balanced now. So we have to perform the necessary rotation, that is your right rotation. So we have to perform the that is LL rotation, that is right rotation. We need to perform the right rotation. So how the right rotation is performed here? So I'll write it here. So we'll be having 30 as our root node, then 20, as our root node, then 20, then 10. Then in right side we have 80, after performing the right rotation, that is in LL rotation, after performing the right rotation, we'll have this value as 60 and this is 40 and here is 80. Now we have to check the balance factor after performing this LR rotation. So this is L rotation, this is R rotation. So these two together forms the LR rotation. So here the balance factor of all the leaf node will be 0. And here the balance factors, height of the left subtree is 1, height of the right subtree is 1. So 1 minus 1, 0. Here the height of the left subtree is 1. There is no right subtree. So 1 minus 0, 1. Here the height of the left subtree is 2 and the height of the right subtree is 2. So it is 0. Now the tree is balanced. Now we have two more values to get inserted, that is 50 and 40. Let us see. So 30, 20, 10, 60, 40 and 80. Now if we want to insert the value 50, if you want to insert the value 50, we have to check with the root value. It is greater than root. So we have to check now this 50 with 60. It is less than 60. So now we have to, it goes towards the left side of 60. Now we have to check this 50 with 60. So this value 50 is greater than 40. So it is placed as a right child of 50. Sorry, right child of 40. So now the 50 is placed. Now we have to check the balance factor after inserting 50 for each and every node. So balance factor for 50 is that since it's a leaf node, for all the leaf node the balance factor will be 0. For the node 40, there is no left children. So height of the left children is 0, height of the right children is 1. So 0 minus 1 minus 1. Here the height of the left is, for calculating the balance factor for the node 60, the height of the left subtree is 2 minus height of the right subtree is 1. It's equal to 1. So it is within the balance factor. So here for calculating the balance factor for the node 20, the height of the left subtree is 1 minus height of the right subtree is 0. So 1. For calculating the balance factor for the root node, height of the left subtree is 2 minus height of the right subtree is 3. So minus 1. So all the node are having the balance factor as 0, minus 1 or 1. So these values are within the balanced factor values. So 50 is also inserted. Next we have to insert the last node 70. So 30, 20, 10, 60, 40 40, 80, 50. Now where the 70 will be inserted? So 70 is greater than 30, 70 is greater than 60, and it goes towards the right subtree of 60. So we have to check the 70 is 80. 70 is less than 80. So it is placed as a left child of 80. Now after inserting the value 70, we have to check the, we have to update the balance factor for each and every node in the AVL tree. So here all the leaf node, the balance factor will be 0 as I told already, because there is no left subtree, there is no right subtree. Here the balance factor for 80 is height of the left subtree minus height of the right subtree is 0. So it is 1 here. Here for calculating the balance factor for the node 40, height of the left subtree, there is no left subtree 0 minus height of the right subtree 1. So it is minus 1. Here for height of the left for calculating the balance factor for 60, height of the left subtree 2 minus height of the right subtree 2. It is 0. So here for calculating the balance factor for the node 20, the height of the left subtree is 1 minus height of the right subtree is 0. So which is equal to 1. Now we have to calculate the balanced factor. Up to this, there is all the values are within the given balanced factor values. Now we have to check the balanced factor for the root node. So balance factor for the root node, which is equal to height of the left subtree 2 minus height of the maximum height of the right subtree is 3, which is equal to minus 1. Now after inserting the given value 70, so we have the tree structure is like this, and after calculating the balance factor for each and every node after inserting 70, we have a 0, minus 1 and 1. So all the values are within the limit of balance factor given value. So now this after inserting all the given values from 20, 30, 80, 40, 10, 60, 50, 70, the final AVL tree is this one, which is perfectly balanced after insertion. Thank you.